I'm just going to share my screen. There we go. And we'll just cut into here. And the first place I actually want to go to is here. Okay, so here's the home page for this module, computational algorithms and paradigms, and a few changes, or additions rather. So I'm going into units eventually. Okay, slight delay. There we go. So I'm going into units, and we have student view, and so we've got everything's the same as per normal, and we're just coming down to now. The first thing I want to point out is there are two quizzes here, and there are 450 odd people in this this particular module. And if I look at the multiple choice for each of these, there is a maximum of, I think, 100. So there's 350 of you who need to be familiarising yourselves with these practice multiple choice questions. Remember, you have a multiple choice assessment. And so these are intended to help you, A, get used to the environment, but B, also test your knowledge with respect to these particular areas. And there are another two that I've prepared that I'm going to add into this. I'll create a section at the top which is called Practice Multiple Choice, and so you'll have 4 in all that you can try over the Easter break. Okay, so that's the first thing that's important to point out. So that's this one, okay, and so you can take the quiz again if you've taken it before, okay, let's go back, and it just gives you feedback on how you're doing, you know, and here's another one on the quantum paradigm. I can take the quiz again, okay, I've got these options, so have a look through those. And as I say, there'll be 2 more coming up this weekend as well. I've got them all ready, so I've just got to load them in. We're in week 5, the week beginning the 22nd of March. So you've been looking at the tutorials, states, gates, entanglement and teleportation. Okay, so that's this particular set of questions. These relate to the quantum part. And the reason you're doing those as well as, well, one, you need to know what they are because I could ask questions about them. So you need to have a good idea of what that's about. But 2, it's also in tandem with the exercises and activities you're carrying out in the practicals with Qiskit. Okay. So that's that. So the practicals, you've got Qiskit there. Okay, so you've got the answers to previous ones. You've got this week's access and the programs that you're looking at in there, together with the actual recordings that are associated with that. Let's have a look. Now, what we want to do today is twofold. So what I've got is the lectures. I've recorded lectures for the logic paradigm, okay, which I also want to look at today because I think Pretty's preparing a demo for the logic paradigm for either during the break or when you come back, so you can try it at leisure. So I've got a recording here for the logic paradigm, which I want you to think about and use, and we'll go through that in a minute. I've also got another area here which is the lecture 5, so that involves algorithms. So we want to start moving into algorithms. and this asymptotic notation and this idea of code complexity. And so there are recordings there for the algorithms and asymptotic notation, and I'll include another one for the code complexity shortly. Okay, and so that's what we're doing. And you've been reading, I've been asking you to read these propositional and predicate logic in preparation for the logic paradigm that's coming up today. Okay, so that's that. Are there any questions? No. Okay, let's keep going then. So what do I want? I want a logic paradigm. Okay, so let's talk about the logic paradigm. We've been looking at a few things. You're familiar with the functional paradigm, and you're also familiar with the quantum paradigm. And from what we've been doing on the pseudocode sort of operations, you're familiar with the imperative paradigm, and you spent some weeks actually just solving problems and getting used to the problem-solving activities. So that's what we're doing there. Somebody's just asked me a question. I'll relate to questions at the end. Okay, let me do this now, and then we'll pick up on questions. Okay, so we're looking at the logic paradigm now. As I said, we've looked at. In fact, we've met the imperative paradigm. We've met the functional paradigm. We've met the quantum paradigm, and now we're looking again at this other one called the logic paradigm, also known as a rule-based approach or paradigm. And so what we're particularly interested in is the logic paradigm with propositional and predicate logic. Okay, so you've been looking at that and you've read that, so you are familiar with that, and that's good, because that puts us in the right place. We want to look at something called the Horn clause, which is related very much to the semantic turnstile that you'll have met when looking through the propositional and predicate logic. And then we just want to pick up with resolution and unification, and for the practical, the logic programming in Prolog that Pretty's going to talk about at 3 o'clock will follow. So, okay then, logic paradigm, also known as the declarative or rule-based paradigm. It emerged in the 1970s in relation to interest in artificial intelligence in particular. And it's different to other paradigms in that the programmer has to declare, or is said to have to declare, the goals of the computation, as opposed to an algorithm through which the goals can be achieved. And the goals are expressed as it says, a set of assertions or rules for the outcomes and constraints. And so you've got this label, rule-based programming. So I could, in essence, set up a sort of a database of rules, if you like, that my system has to comply with, and then I could ask it questions given those particular set of rules that I put in place. Okay. And it is also worth noting that you can do this in other programming paradigms, but the difference here is that with the logic paradigm, and in particular with the Prolog, the approach is built in, if you like. And you can also do things like what are called backtracking, again, which are built into the logic paradigm, but you have to actually program into the other paradigms if you want to use the other paradigms. So the two main areas for application. One is the artificial intelligence approach, and so Prolog is a popular language here, and Bison is another one for expert systems, and CLIPS has also been one that's been considered very popular. Of course, SQL is another application, the database retrieval, so you've got this structured query language, and that's also another language that's considered very popular. We want to focus on SWI Prolog and its applications to what are considered to be natural language processing and to problem solving. And so by natural language processing, we're thinking about linguistics and computer science and artificial intelligence. And we're looking at the idea of interactions between computers and human language, and in particular, how to program computers to process and analyze large amounts of natural language data. Now, obviously, we're not going into great depth here. What we're doing is we're just introducing the concepts. So these are sort of, we're getting flavors, if you like, for the different paradigms and getting some experience of a programming language, from this paradigm. Two noteworthy features of the logic programming approach is that you don't have deterministic sort of system. So if I have an input, it doesn't mean to say that you're going to get a specific output. It could be that you have an input, and when you interrogate it, you get different outcomes according to the way in which the program goes through its program. So you can end up with different answers coming out, but when you go through and exhaust the list of all possible outcomes, then you find that the set of all outcomes are the same. The second thing is that you have, as I said, this backtracking idea where you try to find a solution, and if you come to a dead end, then you back out of the steps that you took in order to realize you've got a wrong answer or an answer that wasn't going to work. And then you try another answer, okay? And then if that comes to a dead end, you come back again towards the beginning and take another set of options. So you're, in a sense, you're brute force searching for answers, in a sense. You're going through these paths until you can actually find a particular solution. So it's this that enables this non-deterministic sort of approach. And this, as I said, is built into the Prolog interpreter and is implicit in all Prolog programs. And if you want to do this in other languages, well, you have to write the backtracking that's required in order to get this backtracking facility available to you. Now, logic paradigm, it uses logic in its program, so it's going to express these specifications for solutions through mathematical logic. And the approach evolved out of the needs of researchers in natural language processing, as I've just said. This idea about automatic theorem proving. Conventional programming languages were found not well suited to the this sort of approach and these needs that in particular researchers were looking for. And so, the language evolved, much as the functional paradigm evolved according to the needs or driven by the needs of the researchers initially. Writing down specifications of a theorem or grammar can be in the Backus-Naur form as a formal logical expression. It provides an effective vehicle, it's said, for theorem proving and natural language analysis in an experimental laboratory setting. So it lends itself to the needs of, in particular, these AI sort of requirements that are developing. So the formal foundations for the logic paradigm are going to involve propositional logic. And propositions, of course, you all know, are statements that are either true or false. So clearly, I've got, I am 21 years old, and another one says I am not 21 years old. Well, either I am 21 years old or I am not. And unfortunately, I'm not. So that's a no. You can't be both 21 years old and not 21 years old. You're either one or the other. No sitting on the fence. Likewise with I am not 21 years old is either going to be true or false. Now, for the backgrounds, I've said see the background slides and notes that I've been asking you to read for some weeks now. The slides are just summaries of the actual chapters that I've put up for you to read. And so I haven't included those this time round. If you want the slides, I can put them up, but they'll be just summaries of the chapters that you've read. And you should have your own summaries of those as you go through reading them. Predicate logic extends this idea of logic to include information about relationships. So a predicate is something of the form manages XY, for example, or bossy X, where X and Y take values from a set of what are called objects in the domain of interest. So if you're talking about manages, you're often talking about, well, does John manage Frank, or does Sylvia manage Bill, or something like that? So you've got manages X, Y. Now, manages X, Y has general variables, and so this is the predicate, if you like. But as soon as you put in the X and Y values, then you've got a situation where you've got a proposition. And so this now becomes either true or false. And again, you'll be familiar with this from the reading that you've done on propositional logic and predicate logic. Okay? Now, what of this horn clause? Well, the horn clause is a particular variation on predicate logic. It underlies, as it says, the syntax of Prolog, and is very reminiscent of the semantic turnstile. So if you look back at the semantic turnstile, you'll see what I mean. And basically, well, they talk about a horn clause having a head, which is indicated by H, and a body, which are a list of predicates. And basically what you've got is that if all the predicates are correct and true, so let's pick up a different colour here. So if these predicates here are all true, then that is true as well. Okay? H is true only if, and only if, in fact, P1 up to Pn are simultaneously true. Okay? So this is the horn clause. And as I said there, yeah, compare this to the syntactic turnstile in the background notes. Now, so here's an example of horn clause. Suppose you want to capture the idea that it's snowing in a city, C, only if there is precipitation, okay, so rainfall, and it's freezing in the city. Then we could have, well, precipitation in the city for C, and freezing in the city C implies snowing in the city C. Okay, so that's that would be an example, if you like, for a horn clause. Any horn clause, it turns out, can be written as a predicate, but not every predicate can be expressed as a horn clause. And so there's a proof for this here that I've given just below. So let's take the first one. Here it is. And we're saying that, okay, A, B, C, D up to G, if all of these are true, then H is true. Okay, and what we want to do is express that as a predicate. So now you can go through the predicates. So the statement here that I've got here, you'll note if you've been reading, is equivalent to this statement here. For that, have a look at predicates in extension. However, you can sidestep this because you can actually go straight from here to this statement here. Yeah? Because you can use the statement that P implies Q, and you'll remember this from what you were reading. P implies Q is equivalent to not P or Q, isn't it? Okay, you remember that from the truth tables, for example. That's one of the exercises given in the truth tables. And so if you look at this, what this horn clause is saying is it's saying that if A is true, A is, well, I've got A, B, C, D up to G. So really what we're saying is if I'll call it P for all of these, okay? So it's A and B and C. So let's see, that's going to be A and B and C and up to G, okay? Then if they're all true, then that implies then if you've got P, if they're all true, then P implies H. And so that's equivalent to not P or H. So either not P is true or H is true. And that implies that you've got not A and B and C and carry on up to G, okay, or H is true. Now, so that's the first step. So you can actually go straight from the first line there, sidestep the C predicates in extension part, and come straight down into this line here, okay? And of course, from that, you've got the result just here, because you've got something called De Morgan's law. You see De Morgan's law. Okay, De Morgan's law, if I can find a space, let me just do that down here. De Morgan's law says this, that not... Now, what have we got? We've got ands, haven't we? So, okay, let me just take that back out. Not A and B is equivalent to not A or not B. And that is precisely what we have just here in this line here. Okay, so we're just following that through De Morgan's law. So if you're not sure of that, check it out, make sure that you're happy with it. And that's the one of the examples for De Morgan's law. In fact, I'll put a capital D there. Okay, and I'll make that a capital. Okay, De Morgan's law, famous mathematician. Particularly if you studied in London, he taught in London. Okay, so that's that version. Okay, then for the second part, and of course that's what we've just finished there is in fact a predicate. What we need then is to show that predicate, give it particular values, and then we can see that it becomes a proposition which is either true or false. For the second part, I want you to look through the proof for this one. You can set up a predicate where every literate person reads or writes. Okay? And this is a problem because if you get something like this example, you get, again, sets in extension, predicates in extension. You get this sort of statement here. And that is going to be expressed in the form, you're either not literate or you read or write, okay? And so what happens is you can't express that as... okay, you're going to get this situation. And the problem is you've got the inclusion going the wrong way. And what happens is you can't express that as a single term on the right, okay, where you've got and rather than or. We've got ors, okay? And what we need, if you go back to the initial statement is, well, in fact, from here, you can see that what you need is these here, where you've got these ands, A and B and C, not A or B. It's got to be A and B. They've all got to be true, not just one or the other, okay? And so what you've got is the statement here, okay, which falls because of that, okay, because you've got an or in them. So that's an example which illustrates that not every predicate can be expressed. Not every predicate can be expressed as a horn clause. So I want you to focus on that particular proof just to ensure you're happy with it. Doesn't mean to say anything about assessments or anything like that. It's all about, do you understand it? And if not, come back with the questions, okay? Okay, so that's the horn clause. And do make, there's the proof on one slide, of course. And what I'd like you to do is also make sure you're happy with the truth tables and in particular the semantic turnstile, okay? The semantic turnstile. How does the horn clause relate to the semantic turnstile? Well, the last part of this set of slides talks about resolution and unification. And so what do they mean by that? These are definitions, really. And so, okay, then, what have we got? So for our definition, then, we've got when you apply this to a horn clause, resolution means that if H is the head of a horn clause and it matches with one of the terms of another horn clause, then that term can be replaced by H. So let's have a look. So we've got, here's one horn clause, okay, and I've just written it as terms. So this could be like the one we had before, A and B and C and D and E and F and G. And here's another one, here's another horn clause, which says that, okay, if T1 is true and H is true and T2 are true, so that means that T1 and H and T2, then T is true, okay? And all they're saying really is, if you're doing resolution, is the fact that you can replace the H by the terms. And so if that's true and that's true, then it follows that that's true, and you can work with that. And we use that in the programming side. So you'll have an example of the Speaks program. So see the Speaks program. Because what you're looking at is you're told that certain people can speak in certain languages. And the question is, well, who can talk with whom? And it starts off as a predicate. And so what you have to do is you run through the database. Okay, and so what you're doing is you're saying, well, okay, if Mary speaks English, if that's your first statement, then in order to be able to talk to somebody, I have to find somebody else who speaks the same language. Okay, so you may go through these, and Mary speaks English and nobody else speaks English until the very last person. Maybe, I don't know, Jack speaks English, and so Mary can speak to Jack. Okay, but Mary can't speak to, say, somebody like Marmy, because Marmy only speaks Japanese. But then if Marmy speaks Japanese and she speaks French, and Mary speaks English and she speaks French, then Marmy and Mary can speak using the language French. Okay, and what this is about is replacing these statements here. So here you've got one where Marmy speaks French, okay, and Mary speaks French, and so they can both speak to each other. But again, what I'm pointing you towards is have a look at this particular example. It's a very nice example to just illustrate this idea of resolution, okay? And it's in the, what you want to look at is the talks with. In fact, that's actually, let's do it like that, talks with, okay? Let's call them X and Y, okay? And X and Y can talk with each other provided they speak the same language. So you establish, you take the first person in the list and see what language they speak, and then you're looking for, you're letting this variable run through all the other people and the person as well the X and seeing who can talk with whom. And then, of course, disallowing somebody talking to themselves in a particular language. Okay? Okay. So that's resolution. In fact, I've just been talking through this example. Here it is. So I could have something like this, you see. Mary speaks English, and I'm looking at who can talk with whom. And so this is my horn clause here, and I'm saying, well, X can speak this language. Okay, so I'm and Y can speak a language, and X does not equal Y. So what you're saying here is, look, this says that X can speak or talk with Y provided X speaks a particular language. Now that fixes the language. So this is now fixed. And so what you have to do now is establish or find somebody Y who speaks the same language. And the other condition here is that X and Y must not be the same person. So you can't have Mary talks with Mary. Okay? The first statement, speaks Mary English, is also considered to be a horn clause, where the list of terms on the right is an empty list. So it's unconditionally true. And a resolution for that, because of that, allows us to deduce that if you look at Mary speaks English, then this line becomes Mary speaks English, and you're looking at Y speaking English, and Mary does not equal Y. So this ties up the first stage. And what you're doing is you're hunting for somebody Y who can speak this language, English. The assignment of variables to values during the resolution is referred to instantiation. Okay, instantiation. So this is where we've got here speaks Mary English. Okay, so you've got that there, but you've got, so you're giving an instance there. X becomes Mary, the language L becomes English, and English there. So this is instantiation. You're giving an instance, a particular example. Still not yet a proposition. We still need to find the person Y. Okay, this one is a proposition because it's either true or false. Okay, and we're assuming that it's true because we've taken it from the database, which is up here on the top. And this one here, though, is still a predicate because we haven't picked our particular value Y. Okay, likewise here. Okay, this is still not completed, so it's predicate. And unification is pattern matching process that determines the instantations possible when making a series of simultaneous resolutions. And so this unification is really what's happening when you're running through all of these values Y in order to satisfy this set of statements here, which lie on the right-hand side of the horn clause, okay? So this is what we're completing in order to establish who can talk with whom. Okay, so that's the logic paradigm. It's an introduction to the logic paradigm. You've been reading about the background logic and you're familiar with what is a proposition and what is a predicate, you know, what are the differences. You're also familiar with all the truth table stuff, and you're also familiar with semantic turnstiles, okay? And we've looked at the horn clause. We've seen that every horn clause can be expressed as a predicate, but not every predicate can be expressed as a horn clause. We've looked at resolution and unification, and then you'll be looking this afternoon Pretty is going to introduce the logic paradigm via Prolog, and you'll see as you work through the exercises for the Prolog exercise, you'll see that they include the Speaks program, so C in particular. The Speaks program. Okay. So I'll stop on that one for the moment. Let's have a look at some questions, see what's happening here. Okay, let's have a look. So we're defining the condition based on the languages they speak. Yes, when you look at, this is Rajalinga, when you look at the program, you'll see that what it's doing is it's a series of horn clauses where you're making a statement of the, a set of database sort of statements. So what you're saying is that individuals speak particular languages. And based on that information, you can then interrogate things like this talks with horn clause. And, if you look at how they're running through the program, what they're doing is you're starting off, say, with the first person and trying to establish who that person can speak with. So then you're looking at who can, if that person can speak with somebody, then it'll tell you who they can speak with. It'll do it one at a time initially, so that's what happens then. And if the first person can't speak to anybody in that list, then you move to the second person and see if they can speak with anybody. And then the third person, and then the fourth, and so forth. Proposition, and that's... yes, that's right. It's either true or false. Quite right, Kash Kumar. Well, the predicate, though, wouldn't be true or false until you gave it values, okay? But it's a description about the conditions required in order to become a proposition. So, for example, you had in the chapters you were looking at, there were chapters about who manages whom in this particular database, and I think it was John was at the top of the list. So that's really what that's really the example to look at with them. Unification. Let's have a look then. Well, unification then is a pattern matching process. So what is this about? This is where you're going through the list of options that were here. Okay, let's have a look. Let's get there we go. Got it. So I can take these out. Okay, at this stage, so let's have a look at this particular example here. Okay, oops, come on. Let's have a look at this particular example here. And this comes from the one up above, so let's clean that as well. Okay, so unification is about running through all the variables. It's a pattern matching. You're looking for those conditions, if you like, or those rules, those horn clauses that tell you that you can, satisfy the thing that you're looking at by replacing the variables by particular instances. Okay, so let's have a look at the one we've got. You've got this, okay, and suppose you've got also got I don't know, speaks. This suppose you also have speaks. Okay, and you've got Marmee, comma, English as well. Okay, so as that was one of the other ones in that particular set of truisms. In fact, they're true, aren't they? They're statements. Marmee speaks English. Full stop. It's true. Okay, there's no conditions that you have to satisfy. So what you're doing, given these rules, of which there may be more, okay, so I'm thinking of these speech rules here, you're then looking at this particular question here, okay? Who can talk with whom? So this bit is really asking, who is it that can talk with whom? And so people can talk with each other, provided the first person speaks a particular language and the second person, Y, also speaks the same language. And the first person is not the same as the second person, okay? So you're looking for particular X and Ys that speak the same language. And so let me just do that. Sorry about that. Let's come back again. So that's what you're looking for. And so if you look at the first one, you give it an instance, okay? So the instance is, you give it the value Mary. So that's an instance. And you get a language out of that, English, and that forces English to go into that language there. So if you compare the bottom of this slide with what's here, and this one value here, you're giving particular instances. And now you're looking for pattern matching. So this is the unification part. What you're looking for is unifying those people who speak English, because that's the language that you're using to communicate or talk with each other. So that's the unification. You're unifying all the people, grouping, if you like, all the people together who speak the language English. And so eventually somewhere, because of what I've just written in with Marmee speaking English, then you could replace Y with Marmee. Okay? And Marmee would not be the same person as Mary. Okay? But that would then satisfy that, and you could say, well, okay then, Mary rather, can speak with Marmee. Okay? And there's your unification. Okay, so that should, does that help, Sweetie, and Cash Kumar? Yeah, good. Okay then. So that's that. Okay. Nice approach. It's a very good problem. Also, backtracking. When you look at backtracking, there's a very good problem for that, which is the N Queen problem. So I could say this, for backtracking, see, for example, the N Queen problem, okay? And this is about, well, okay, if I've got an 8x8 chessboard, for example, how many queens can I place on the board so that no queen can take any other queen? Okay? And you could do that for, in fact, not just an 8x8. You could do it with a 1x1, a 2x2, a 3x3, a 4x4, a 5x5, a 6x6, and so forth. And so now you've got a problem, okay? And you've got a problem that you can solve from your problem-solving skills, and you'll notice that how you're getting your solutions is you try to place the queens in different positions so that they can't take each other. And that's an example of backtracking, because what am I doing? If I've got a chessboard, okay, let's put some rows in. There's 8. It's a bit... there you go. Now, as soon as I put a queen, say, in here, then you can't place a queen in here, and you can't place a queen in here, okay? And you can't place anything in there, can you? Whoops, and that should go there as well. 1, 2, 3, 4, 5, 6, 7, 8. Okay, gonna drift there. So now you're looking at different places. So if I put a queen here, okay, where else can I put a queen? And what you're trying to do, in fact, is get 8 queens, because 8 queens will fit on there. And if you put one in the wrong place, you know, suppose, although you can't put them in here, suppose you put one here, okay, instead of here, then you say, no, I can't do that because the queen can take me, okay? And so what you're doing then is you're saying, okay, I can't sit in that position, for example, because then you'll say, I can get you. So you back out of that. You'll back out and say, okay, maybe I'm going to put it into the next one, you know. But every time you put it in one of these down below, you're going to get taken, you know, here or here or here or here. So this is backtracking. You're trying them randomly. Well, in an ordered way, in fact, going through there. And then maybe you'll start the next one. Try there. No, I can't go there. How about there? Yeah, I can go there. But that may lead to there being less than 8 queens that you can place on that board. And so if that's the case, then you might have to come out of that position. So you're backing out of a solution that you were initially happy to try. And so you're going to keep... taking these particular positions out of play until you can optimize the situation and get 8 queens on the board. Yeah? Yeah, it's a good problem, yeah, Mohammed, yeah. Excellent, yeah. Yes, you can think of it in that way, yeah. It's a good problem, isn't it? Yeah. And, you know, if I was approaching it, I would start with, you know, n equal 1. How many queens can I get if I've got a square, 1 square? Well, number of queens, 1. You know, and if I've got a 2 by 2, I can put a queen there. That means I can't go there, I can't go there, and I can't go there. So now I know 1. Okay, and then you try a 3 by 3. And just keep going in that manner, you know, 1, 2, 3, 1, 2. So if I put one there, I can't put one in there, or there, or there. So I can put one here, okay, but then I can't put one anywhere else. And I can put one there, but then I have to remove the other one. So at the moment, it looks like 2. But again, maybe there's a problem with where I started. So maybe I have to start trying in different positions to see if there's any sort of configuration that will allow me to get more than 2 queens on that particular board, and so on. Okay? Okay, so let's move that one. Okay, so let's take a 10-minute break. Okay, we'll come back at 2:05, and then we'll start looking at algorithms, okay? So that's the next topic in line, algorithms. Okay, everybody, let's get going. I'm just going to start recording again. So again, if you don't want me to record, please say so. Interesting conversations taking place. Good. Okay, so I'm just going to go straight to algorithms if I can find it. There it is. Okay, so in this discussion, we're just going to take an introduction to algorithms, and then I want to move towards asymptotic notation in the second talk. Okay, so these are already recorded, and they've been put up on StudyNet or Canvas, if you like, for you to refer to. So, okay, then let's go. Okay, so we want to look at the idea of algorithms, coming up with some sort of definition for an algorithm with some examples. And we just want to focus in on today just two examples of search algorithms, one being a linear search algorithm, which is a very, very well-known algorithm, and then comparing that to the binary search algorithm, which again is another well-known algorithm. And both of these start to introduce this idea of the big O notation, which is what we want to pick up in the second talk when we're talking about this asymptotic notation for solving problems. Okay then, so let's have a definition. Well, from the book by Menezes, Van Oorschot and Vanstone, called The Handbook of Applied Cryptography, which I might add is freely available to download on the internet. Or if you like, you can spend a lot of money and get a hardback copy. This book is a well-known book. It's updated regularly on the internet, and has the following definition for an algorithm. An algorithm is a well-defined computational procedure that takes a variable input and halts with an output. Okay. So the phrase well-defined computational procedure is not considered a sort of mathematically precise enough sort of statement. It can be made precise if you use formal computation models such as the Turing machines or Boolean circuits and logic gates. Okay, so this is again from the Handbook of Applied Cryptography. Intuitively then, you can think of an algorithm as a computer program written in some specific programming language, written for a specific computer that takes a variable input and halts with an output. So this is the stance taken again with the Alfred Menezes, Van Oorschot and Scott Vanstone's book. So we would like a more formal or more like a more precise formulation for the concept of an algorithm. And we turn at first into the Church-Turing thesis. So this was a thesis that, again, I would imagine that you're well familiar with, in which Alonzo Church and Alan Turing both independently came up with the same type of observation and published on that. So independently, they put forward what's become known as the Church-Turing thesis, which says or states that the class of functions computable by a Turing machine corresponds exactly to the class of functions which we would naturally regard as being computable by an algorithm. And it was felt that this captured the intuitive concept of an algorithm in a mathematically precise definition. Okay, so that was the stance taken. And it introduced, with lots of others, I might add, fundamental notions for the modern theory of algorithms and hence computation. And it's said to have laid the foundations for the modern theory of algorithms and the modern theory of computer science. Okay, so let's have some simple examples then. Nice question. Somebody's just stated, Mohammed. Why do these mathematicians always want to make things unintuitive? Well, clarity. Okay, anyway. Okay, we meet various algorithms, or we go through various things in life and that we could think of as algorithms that we go through, sometimes unconsciously, such as making a cup of tea. Now, there are different algorithms for that according to whether the milk goes in first or last, and so forth. But there are steps that you can employ in making a cup of tea. And you have to decide upon, lots of questions such as, does anybody actually want a cup of tea? What sort of cups and saucers or mugs are we going to use? Do we have a kettle? Is the kettle got water in it? Do we need to put water in it? Do we have any tea? What type of tea do you want to use or give? There are lots of issues that you can extend or incorporate rather into your algorithm to end up with a cup of tea. Ones that we meet early on in life in mathematics is the addition, subtraction, multiplication and division rules. So we go through these steps. It's a step-by-step process, as you say, that we employ to achieve the addition and subtraction and multiplication or division of two numbers, these being binary operations. An early programming sort of exercise, and I mean early, is changing a number, say, from miles to kilometres. Okay. Another one that we meet that starts to become useful in the security area is finding the greatest common divisors of two positive whole numbers. And of course, Eratosthenes' sieve, or prime sieve, which is an approach or an algorithm for deriving the first 100 prime numbers, if you like, and you've got this idea of where you take the first number 1 and you say, that's not prime, so I'll cross that out. Next, I take the next smallest number, that's 2, and that's going to be my first prime number. It's not divisible by anything other than itself and 1, okay? And so they're the only two, so it fits the prime number definition. 1, of course, is excluded from being prime because it's called a unit, and it's convenient to remove it, so that's what happens there. So you've got 2. So you move to the next smallest number, which is 3. But before you move to the next smallest number, you need to do something. What you need to do is get rid of all multiples of 2. Okay, because they cannot be prime, because not only are they divisible by themselves and 1, they're also divisible by 2. So you get rid of all the even numbers. And then you start looking at number 3. That's the next prime, and so you get rid of all multiples of 3. And then you move to the next number that exists, which is number 5. You say that's prime. And now you get rid of all the multiples of 5. And so you carry on. And so that's Eratosthenes' prime sieve. Again, a step-by-step procedure. So here's a couple of ways that people write their algorithms. Cryptographers, for example, prefer the bottom approach, but you can also write it in statements such as the following. What are you going to do if you're going to change miles to kilometres? Well, first of all, you have to get the distance in miles. And so that's the first step. And this is what you're getting here. And you're putting this into the variable big M. And you then convert your distance to kilometres, step 2. And that's said to be 1.609 times the distance in miles. So you take your variable m, the value held in that particular slot, and you multiply it by 1.609, and you store that value in the other variable location, which we denote by k, for kilometers. Okay, so that's that step done. And then, come on now. And then you move to step 3, which is display the distance in kilometers. And so you get your output from the variable being posted to the screen, if you like. Okay, so that's one that we've met early on. Here's Euclid's algorithm, which is for finding the greatest common denominator of integers, two integers a and b. And this one is one where you have your a and b. What does it say? It says store the values a and b in the memory locations denoted by the variable a and b. And then you look at the b value. And you say, if b is 0, then return the greatest common denominator of those to be the value that's sitting in a. Now, that's a bit unusual at this point, because you'd say, well, okay, if I'm looking at the two numbers, if I'm given two numbers and I want the biggest number that goes into those, or the greatest common divisor of those, then I would expect a and b to be non-zero. But of course, okay. So what you then do is you take the value in a and mod b. So this is from moving from step 2 to step 3. You're saying if b is 0, do this, else move to step 3. So step 3 is, okay, put the value that you've got for your a value, mod b. So in other words, you're dividing your a value by b and putting the remainder, so this stands for remainder, just there. You then put what's in b in a, you put the remainder value in the b value, and then you go back to step 2. And you keep going round. Okay, keep going round until you can get out. Okay then, so that's all very well. Let's have a look at an example. Okay, so what this is doing is saying, okay, if your two first values are a and b, you will have some sort of remainder. So this is the division rule that we're using here. Okay, so if you look that up, we'll find that under the heading of division rule. So what are we doing there? If I've got something like 10, if a equals 10 and b equals 7, then I'm saying that 10 is equal to 7 times 1 plus 3. Okay, so there's my b, there's my a, and here's my remainder r. And then what you do is you move to the next line according to the algorithm. You say, okay, what's in there goes there. And let's see, what's in here goes just there. And these Q's are just multiples, really. Okay, and you proceed, you carry on like this, and you keep doing it. So the next one would be, well, okay, then the next line I would get would be 7 is equal to 3 times 2 plus 1. Okay, so I put my 3 there, I put my 7 just there, and I've recalculated. Okay, and then the next time I would take my 3 and put it there, and I would take my 1, and that would be 3 plus 0. Remember, this is the remainder, this is b, and this is a, the new a. And the next line says I'm going to have 1, and that's going to equal, because I'm taking the 1 there. The next line, I would have my b value there. So that's going to be times whatever you like, any number you like. And then you're going to add 1 to it. And that's your, and 1 to it. And so what you've now got is a, b, let's say 1, the multiple, plus r, And now you can see that B at this stage is equal to 0. So now you've got this situation where this line makes sense. Okay, and so you can come out and say that A is the greatest common denominator. In other words, 1 is the greatest common denominator in this particular case. Yeah? Now, so that's summarized by that statement there, okay? And here's an example which illustrates it a bit better, okay? So what you're doing is you're saying 63 is 1 times 35 plus 28. You're then moving the 35 to there, and you're moving the 28 to there, and then you're recalculating just here to get 35 is 28 times 1 plus 7 left over. And then you do the same again, okay, again according to Euclid's algorithm. So the 28 goes here, the 7 goes here, and then you find you get a remainder 0. So this is your new A, your new B, and your new remainder. And so the next line that we should put in for Euclid's algorithm would be 7 is equal to 0 times whatever you like, let's call it 1, plus 0, isn't it? And so now A is 7 and B is 0. So now you've got the line 2 condition, okay? B is 0 just here. And so you can come out. A is the greatest common denominator. So for us, A is going to take the value 7. Okay, this one here. Okay, the algorithm works. It's a nice algorithm, but you can also solve it using a product of prime numbers. And here's a way of dealing with that. You can sort of look at 63 and you can say, okay, 63, that's 3 times 21. Okay, and 21 is 3 times 7. So what you've really got there is 3 squared times 7. And here, 35 is just 5 times 7. So if you compare the two, what have you got? You've got 3 squared, okay? The 3's are in the 63, but there are no 3's in the 35. There's a 7. That's the only other number you've got there. And there is a 7 here. So you've got now this common value, this common number that will divide into both of these. It's the biggest number. The highest common factor is 7. And the highest common factor is the same as the greatest common divisor. Okay? And so you can see that follows through quite nicely and confirms the result that we found here using Euclid's algorithm. Okay? Now, search algorithms then. So let's look at this one. It's a sequential search algorithm. So you've got a data set, okay, and you're hunting for a particular value. And let's say there are no repetitions in this one and that the data set has a size n. Then the best possible thing that could happen as you search through this algorithm for your particular value is that on the very first attempt, you find the value. Okay, and so the minimum size for your search is going to be 1. However, it could also be the case, the worst case scenario, that the last member of the data set that you look at is the value that you're seeking, okay? In which case, the worst case is you have to search every single one, and it's only the last one that is the value that you're looking for, okay? So you've got a minimum, you've got a maximum. So the question then is, well, on average, how often would you expect to have to search through a sequential search algorithm? How often would you expect to have to search before you actually, in general, find your particular value that you're seeking. And it turns out that the expectation, so this is the expectation, is n plus 1 over 2, where x is the attempt number, if you like, for finding a match. And because of that, we say that the linear search algorithm runs in big O n time. Okay? Now, how do we prove that? Well, we go as follows. Here's the first part here. So the E in this value here is normally written in what's called blackboard E, which is like so, and the X value would be like so. So let's have a look. Now, theoretically, we would say, and you could look at this from just a mean average, if you like, as well. Just use X bar. But I'll stay with the experimental, the theoretical mean average. Okay, so that's the. In fact, let's make sure we know that. This is the theoretical mean average. Okay, as opposed to the experimental. X bar is said to be the experimental mean average. Okay. Or mean average is the other name just for the experimental mean average. So let's have a look at this. So what we've got here is, okay then, this theoretical mean average is defined to be the sum, as in the Excel idea of summing, from I equal 1 to n, because there are n values in there, of the probability that you'll take the value xi times xi. And the probability pi then is going to be the probability of finding a match at the attempt x subscript I. So if you've got x subscript 1, that's the first go, x subscript 2 is the second go, x subscript 3 is the third go, and so forth. Okay, so what have we got? Well, if you're looking for a particular value and every one of those values are different, then the likelihood of finding your value is going to be 1 over n. There's only one chance, there's only one successful observation you can make, because there's only one value of m there. And you're dividing that by the n values that you've got. So it's 1 over n. And so this is where this part comes from. Okay, the probability is going to be 1 over n. So that's that. Now this leaves us with our sum of xi's, because we're summing. And so what you've got is 1 plus 2 plus 3 plus 4 all the way up to n. Okay, so that's what's going on there. And the question now is, well, okay, what does that come to? Because it turns out what it comes to is n times n plus 1 divided by 2. Let me just tidy that up so you can sort of see. I'm thinking of this n here. Just make sure it's an n. Okay? Now, so that's where that comes from. Now, to see that, what we need to do is proceed as follows. Okay, so that's the result. That's the result, n plus 1 over 2. Now, to see that, let's call this sum. I'm going to forget about the probability part. I'm just going to focus in on this part here. Okay, in other words, it's coming out. There it is. 1 plus 2 plus 3 plus 4 up to n. And I'm going to look down here where I've got the word note. Okay, so that's coming through now. Now, I'm going to call this sum on the right-hand side, 1 plus 2 plus 3 plus 4 up to n. I'm just going to call it S subscript n. Okay, and that just means that S for sum and n means I've got the first n natural numbers that I'm adding together. Now, okay then, The great thing about maths is that you can add numbers together in any order you like, okay, as long as they're the same numbers, and you don't change the total. So I could equally well write my sum, Sn, in the second version here, and start with n, then n plus n minus 1, then n minus 2, then n minus 3, and carry all the way down until I got to 1. Now, that's quite useful because if I sum the left-hand side, what I get is 2Sn, double the sum. And what's really interesting is that when I take the first column here, because I can add numbers together in any order I like, so I choose to add them column by column. And here, if I add these two numbers n and 1, I get n plus 1. So that's that value just coming up now in a minute. I'm just waiting for it to come through on the screen. Okay, so that's the first one. Let me just ring it. There we go, finally. Okay, so if I add the n in the column above to 1, I get n plus 1. But hang on a minute. If I move to the next column, I get n minus 1 here plus 2. Okay, n minus 1 plus 2. And so that gives me n plus 1 again, just here. And if I go to the next column, I get n minus 2 plus 3, and that gives me n plus 1 in the next column here. And if I take n minus 3 plus 4, I get n plus 1 again. And if I carry on doing that, let's look at the other end. At the other end, I get n minus 1 plus 2, which gives me n plus 1. Okay? And finally, in the last column, I'll get n plus 1, giving me n plus 1. Okay, and so that's going to give me the last one there. Okay, so what I've got, in fact, is lots of n plus 1. All the columns add up to the same value. So the question then is, how many have you got? Well, this number, Sn, that I started with here, okay, that one starts at 1 and it finishes at n over there. Let me just see now, it's just coming. There we go. It goes from 1 up to n. The arrow's pointed. So that means I've got n lots of n plus 1. And so that's what you've got just in the next line there. But of course, that's double the sum. I don't want double the sum, I want the sum. And so I have to divide both sides by 2 to get the sum of the first n natural numbers. Okay? And so what I've got is what I claim to have. And so what we've got is the answer here, which is n plus 1 over 2. Okay? Right, so that's that one. Let's take a look now at, here's an algorithm for it, a linear search algorithm. It's not the only one, but let n equal the number of elements in the data set. And for I, defined to be n, you step down in steps of 1, and so you're going to have an array, and if you're looking through, you're starting at these, you're sort of saying, well, okay, if the value in the ith position of your array is x, the value that you're searching for, in other words, then you quit the loop. But otherwise, you go to the next value of I, so you're going to decrease, and then when you find the value you're looking for, you return it. Okay, so that's that. How about the binary search algorithm? Well, the binary search algorithm is going to be, it turns out, of order log base 2 of n. Okay, so what we have here is we're going to use what's called a divide and conquer. So the first thing we have to do is assume or go through the workload of ordering the database. And the idea here is to take your values in order, and you take the median. You find the median, which is going to cut the data set into two halves, essentially, okay? And you either capture your value, the value you're looking for, okay? So in other words, you've only cut this thing once and you've found it already. Or it's either going to be in the upper half or the lower half of what you're looking at. So what you're doing is you're taking your values from 1 up to n. Let's call it 1 up to n. Okay, and suppose we've got a value here. Let's do it as a blob. Then what you do is you cut this in half. So I'm going to use an x for a cut in half. And you say, this value that I'm looking for, x, is it in the top half or the bottom half? And you say, it's in the bottom half. Well, in that case, then, let's focus there. X is actually, let me change that value of x to m, only because I'm going to use x in the next slide. Okay, so I'm looking for this value m, okay. I cut the interval from 1 to n in half, and I say, it's in the lower half. So I throw away the upper half, ignore that, and work with the lower half, okay? I'm just going to keep my m there. And then I take this and I cut it in half. I find the median again, and I say, is it in the upper half or lower half? And you say, it's in the lower half. So there you just look at that and you throw away that. And then you say, I'm going to take the median again, so I'm going to cut again. And you say, is it in the lower or the upper half? And you say, it's in the upper half. So now you take that and you carry on with that and you throw this away. And so that's the binary search. You keep iterating in until you lock on to the actual value that you're looking for. Okay? So that's the binary search algorithm. So a reasonable question is, what's the number of times you're going to have to do this? Well, let x equal the number of times that we have to cut the range, if you like, of possible values in half as we home in on the value being searched for. So here's a diagram that illustrates what I've just been talking about. So here's an example. And so what you're actually doing is essentially cutting the range of values, the intervals, into intervals of size 2 to the power x, where I've taken x here to be 1, where I'm taking my first cut here, the first median value. Then I let x equal 2. That's my second value, okay, when I use this one. And so now I've cut, essentially, if you took the whole thing up to n, you'd now have 4 intervals, wouldn't you? 1, 2, 3, 4. And that would be 2 to the power 2 equal to 4 intervals. Here I've got 2 to the power 1, and so I've got 2 intervals. Here's the first interval, here's the second interval, okay? First interval, and here's the second interval, that's right. And for the 4 intervals when x is 2, I've got 1, 2, 3, and the fourth one there, 4. Okay, so this is what's happening. So the question is, okay, how many times am I going to have to cut before I actually find the value n? And what you have there is the following. Okay, so we're going to keep cutting these range of values until there's only one interval, until the only thing that contains m is a singleton. So it's the only element in the set. And so what we have then is we're going to have 2 to the power x intervals, where x is the number of times you're going to have to cut this interval to home in on the value you're after, which is, let's say, m. And so what you actually have is the following. 2 to the power x is equal to n. That tells you how many intervals you've cut the large interval 1 to n into, okay, before you found the value you were after. And so in that case, okay, it follows that if you take logarithms, okay, so you may have to look up logarithms just to refresh your memory, but you take the logarithm, and we're going to use it base 2 of the left-hand side, 2 to the power x, and that's going to give you the logarithm, base 2, of the n value. You can see already there's the log value there that we're actually looking for. And by the properties of logs, that means then that this log base 2 of 2 to the power x is the same as x times log base 2 of 2. Okay? And on the right-hand side, we've got this log base 2 of n. And of course, log base 2 of 2 is just 1. Because what this actually corresponds to is what power of 2 do I have to, what power do I have to raise 2 to in order to get 2? So if I said, so the corresponding index version of this logarithm is 2 to the power, let's call it y, is equal to 2. It implies that y is equal to 1. Okay, so this thing here actually equals 1. And so what we get is log x is equal to log base 2 of n. And so we're finished, basically. That's the answer. And it turns out, from what we're going to talk about next, that x is then, in terms of big O notation, it's bounded above by multiples of log base 2 of n. Yeah, log base 2 of n, Mohammed, that's right. Excellent, excellent. Okay, so complexity theory then. For computational complexity, we're interested in whether a problem is solvable or intractable. Often, if we're looking at cryptography, for example, if you look at RSA, the Rivers-Shamir-Edelman sort of algorithm, you've got what's there is considered to be an intractable problem, an NP complexity problem. However, if you move to using Shor's algorithm in a quantum environment, then you find that it's solvable in a sort of P time, okay? So P complexity. So it depends on the environment in which you're working, in this case, as to whether a problem is solvable or intractable. If you're using classical techniques or techniques based on classical numbers and classical mathematical approaches, then it's the RSA problem is considered to be an intractable NP problem. And so what we're interested in often is the size of the resources required in order to solve the problem. And from the perspective of time complexity, you're often you consider the relationship between the input size and the number of steps required to solve a given problem. And then you look at how long does it take to carry out those particular number of steps. Cryptographers then, they seek an intractable problem, what's called an NP problem. And cryptanalysts, the people who are trying to break these algorithms, they look for a tractable problem, a solvable problem. And Shor's algorithm, given you can get a quantum computer with sufficient processing power, will break RSA. Okay, from the perspective of space complexity, you often consider the relationship between input size and the amount of memory required to solve a given problem. And again, this leads us to these complexity classes such as P and NP type problems, tractable and intractable problems. And it allows us to compare algorithms to determine efficiency, for example, in the runtime and space required by different algorithms. And if you were looking, at, say, comparing algorithms, as they often do, NIST, the National Institute of Standards in the States, who look at algorithms, so they recommend algorithms for a 5-year run period, and then they have to recheck them and make sure they're still fit for purpose. they will have, say, many contenders. And what they have to do is look at the efficiency. You know, how fast can they encrypt and decrypt? How much space do they require? These are issues that they're particularly interested in, and so these upper bounds, these big O notations, start to matter from a comparative sort of perspective. Okay, so that's the first introduction then to algorithms. We looked at some definitions. We looked at some straightforward, simple examples. We looked at the search algorithm and seen that it has complexity big O(n). And we've seen that the binary search algorithm has complexity big O log base 2 of n. And we've just made a mention about complexity theory, where we're interested in particular in runtime and space. Okay. Okay, so that's the first part there. Are there any questions? I see that there are a couple of questions. Let's backtrack on those. Let's have a look. Okay, some questions on prime numbers. Okay. That's right. Okay, let's have a look. Oh, how can 12 be expressed as a product of prime numbers, of two primes? Well, it doesn't have to be a product of two primes. It is involving two primes, which are 2 and 3. It's just that you're raising 2 to the power 2. In other words, you've got 2 times 2 times 3. And the idea of representing representing any number in terms of primes means that you may often and are predominantly interested in more than one prime, or involved in more than one prime being multiplied together. So, for example, if you had 2, 3 and 5, for example, that would give you, what, 6, 5 is 30. So 30 would be an example of one that involved 3 primes. Yeah, that's fine. And you could have any number of powers of them. That's 3 numbers, not 2. That's okay. That's not a problem. We're looking at expressing numbers as a product of primes. No, that's not true. It's, let's have a look. No, it shouldn't do. Let's have a look to see that then. Let's have a go. Here we go. So let's have a look. We're looking back then. Primes. Where do we have primes? So not on there, is it? Okay. So Mohammed, I'm trying to answer your question at the moment. Okay, this is where we're looking at product of primes. Okay. No, there you go. No, we just said that every integer may be expressed as a product of prime numbers, not how many prime numbers. Okay. Is that okay? So let's... Of course I'm right. Sorry, Mohammed. Let's have a look. Any others? Yes, that's right. 63 would be 3 times 3 times 7, which is what we had. And that is a product of prime numbers. 3 is prime, and so is 7. So you're multiplying prime numbers together. And product multiplication. Okay, sweetie? Product is multiplication. No, it's not a sum. No, it's a product. Yeah, binary is log base 2 of n, isn't it? That's right. Well, what you're looking for, yeah, it's a good question. Kash Kumar, how is time and space complexity affect the algorithms? Well, what you're looking for is often something that's very fast. So, for example, if you're looking at a hash algorithm, you're looking to have a function that performs as fast as possible. In fact, you're doing the same with encryption and decryption. You're looking for functions, algorithms, that perform as fast as possible and take the minimum amount of energy to do so. And in particular, you can see that if you're looking at, say, the Internet of Things, where you haven't got much power, okay, so you can't support a lot of resources. And if you're working with the Internet of Things and you're trying to encrypt things, what you're trying to do is you're trying to achieve that encryption, that scrambling of the data very quickly so it doesn't use too much energy. And you're trying to use up as little space as possible because you haven't got the space as well. Okay, so that would be an example where you're particularly interested in time and space complexity being very low, really. Yeah. The advanced encryption standard was an example of an algorithm that replaced the data encryption standard. And these were used for scrambling blocks of data. And the advanced encryption standard was compared on these two particular aspects, amongst others. And it far outperformed any of the other contenders for the position as the advanced encryption standard. It was called RINDAL, the particular algorithm. And again, what it did is it encrypted very fast and it used up very little space in comparison to the other algorithms that were being proposed. Hash is almost big O1. Okay. Yeah. I mean, most of the hash algorithms use SHA now, the simple hash algorithm. The MD5 algorithm, for example, has now been dropped because it has too many problems with collisions and so forth, because it takes input, plain text, if you like, of any size, but it outputs a fixed value, which is much smaller than the size of the plain text. And so you get different plain text having the same output. That's called a collision. And what you're trying to do is minimize, with a hash function, you're trying to minimize the possibility for collisions whilst achieving the hash value as fast as possible. Yeah. Okay, how much time have I got? Running out of time. Let me just show you some. I want to move to the following, okay? So I'm just going to do this and then we'll take a quick break. What I want to do is just record this. I'll see how far I can get with it. No, what I'll do is I'll stop there. What I'll say is this. Okay, what I want you to do is the following. So let's start sharing the screen. Okay, and then we'll take a break because Pretty will be here in a moment. Now, we're coming up to this 2-week period, okay, where there are no lectures, and that's okay. It's a good opportunity for really getting into the revision and really starting to get prepared for the assessments that are coming. And what I want you to do is to start looking ahead. So what I'm trying to do at the moment is I'm trying to put in place recordings of the lectures that I would give. And what I want you to do is to actually, yeah, that's me. Thank you. What I want you to do is look through these recordings. So I'll be uploading these as we go through the next 2 weeks as well. Okay, that's my intention. So let me just, because you're seeing my view, which is got stuff under construction as well. So let me just start the recording just to make sure that everything's okay. Okay, there we go. So I've just started recording. I'm coming back in. So that's done. I'm out of there. I'm into there. Right. So here's the units folder as you see it. We're just looking at. In fact, I've got week 5 at the top here. Okay, so I have started to move these around so that we can see these. And what I want to do, first of all, I'm going to start again. Why is that? Because I'm in semester A's rather than semester B's. I apologise for that. They're next to each other. It's very easy to hit the wrong one. Okay. So here we are in the correct version, semester B, and we're looking at units. I'm going to go to your view, and here we go. So what we've got is week 1, week 2, week 3, week 4. Don't forget these practice assignments. There are another 2. I've already written them. They're ready to go. I'm going to release them as we go through the next 2 weeks, under the assumption that you will also be looking at the slides that I'm going to produce. So the logic paradigm, I've already got a recording there for that, okay? And so that's ready for you to look at, just to aid your memory. And for the complexity ones that we've just started, okay, so that's in week 5, I've got algorithms, RAM, asymptotic notation, and complexity. Okay, I've got 2 of these recordings up. Here's one for the one that we've just done, the algorithms one. And the second one here is of great interest as well because it deals with what we call asymptotic notation. And the thing about asymptotic notation, I'd like you to look at that set of slides, okay, where that's discussed. And then I want you to try the exercises that are actually given in here. Okay, so this is the discussion. These are the slides. And towards the end, we get, here's the definition for best, worst, and average case complexity. So you need to know these definitions, okay? So that's slide 12. Mark slide 12, okay? And so we end up then with these different cases where if you've got a function, let's call it f of n, then here is the lower bound. I found some value n0, and for all values of n greater than that, my function g of n is smaller than that. Okay, and so I say that's going to be big omega. So that's omega n. Whereas if I want big O n, sorry, then I need to have, here's my function. Okay, here's my function. Oops. Okay, I can't get this on the... No. Here's my function, f of n, and now I've got an upper bound, k times g of n, and it's, so what I've got is for all values greater than n0 on the x-axis, or the n-axis in this case, the function is smaller than the k times g of n. And so we say that the function f of n is of the type big O g of n, okay? Now, the questions I want you to familiarise yourselves with are these type of questions. So you need the definition. You need to have listened to the slides, the recordings. And then you have 9 questions there. And I want to know, are they correct? Are they true? And why? And which ones are not true? And why? Okay? And that's quite a useful thing. If you can get ahead on that, that's great. We can crack on. Okay, so that's the first exercise. The second one, sorry about that, the second one is to look at this code complexity, this one here. And I'm going to record something for that, okay? And I'll put it after the asymptotic notation. So that will be the next one that's coming out, okay? And that will come out within, well, it'll probably come out over the weekend, okay? So for next Monday, that will be in place. So I'd like you to look at that as well, okay? So that's 2 for you to look at. Okay. We've already done algorithms, so I would look at that just to refresh your memory. But the 2 I want you to look at are the asymptotic notation one and the code complexity that's going to follow that. Okay. And then you can have a go at the practice assignments or practice multiple choice questions that I'm going to publish also shortly. Okay. There'll be 2. One will be on asymptotic notation and complexity, and the other one will be on logic, the logic paradigm. Okay, so any questions? Yes, that's right. It's good practice in order to understand complexity. Kashmir, yeah, that's right. Yeah, I mean, you know, it's like everything. I mean, they are interesting problems if you like that sort of thing, and I'm assuming you do because you're here, okay? But anyway, have a go at them. If you get stuck or you want to ask me questions during the Easter break, what I want you to do is publish them on the discussion forum and also send me them through the Canvas email because then I can see them, okay? That would be very useful, okay? Is the highest degree of the polynomial the big O? Often it is, actually, yeah. Or you can say any polynomial with a larger degree. So if you've got a cubic, then you can say that this is a cubic, big O, you know, x to the power 3 or n to the power 3. But it's also big O n to the power 4 or big O n to the 5 or big O n to the 6 or anything in between, you know, between 3 and wherever. Yeah. Okay, so I'll stop there. Don't forget that, though, but, you know, keep revising. You know yourselves that there's not long to the assessments, and so what you have to do is keep on board, but don't burn out. You know, just keep, you know, play well, but work well as well. You know, make sure you're prepared for the assessment. Give yourselves the best chance possible. What I'll also do, and can if I say, can all of you just email me to remind me? I'll do this for Monday. So I'll try and do it before Monday, but certainly for Monday. I will also publish a set of questions, okay? And I'll email you when I've published them. And in fact, I'll try to incorporate them in the email. So please read your emails, you know, when I send you them. And that will be some questions for you to try, okay? And then we can discuss those when we come back. We come back on the 12th of April, don't we? So we can discuss those that week. You need to look at the module guide. Let's actually do that because I'm now concerned to make sure that it doesn't come too early for us. Okay, so what I'm planning to do is, yeah, week 40. That's when we'll do the online class test, okay? And week 40, you'll note, I always have to do this because I never remember. You have to look at the indicative content. And week 40 is going to be the week before the assessments begin proper. You know, and by that they mean the AAA assessments, the replacements for the exams. So we'll have an in-class test in the week beginning the 26th of April. So that'll be 26th, 27th. It'll be the 29th of April, won't it? If we hold it on the Thursday. We'll try and do it within this session. Okay? The final assessment I'm planning for, I've put it together an assessment that involves 2 questions for the 60%. Each question is worth 30%. But I've got two versions of the test because I have to get the internal moderator to approve it or agree to it. So if the internal moderator doesn't like me setting two questions, there shouldn't be a problem, in fact. But if he doesn't, then I've got a backup, which is 3 questions. It's an online test. Yeah, it's online. So it's an open book, online test. So you get the assessments then will be twofold. You'll have a multiple choice question, sort of quizzes, like the practice ones, but there'll be a real one. They'll be in the assignments folder, and that will be worth 40% of the overall value. So if you go back to the module handbook, you'll see just here, you can see, look, the first assessment is the online classical test. The online class test, and it's an MCQ, it's a multiple choice question, which is going to be put together on quizzes, and that will take place, its set week is week 40 and the hand-in week is week 40. It's timed, okay? So it's going to be timed. And the online assessment, number 2, will happen in week 41, and I'll put TBC just to say to be confirmed, but that's what I'm aiming for. And I haven't had anybody stop me or say no yet, so it looks like that's going to be okay. And yeah, so that's how it's going to be. Okay, so there's the information just there. Okay, they're both online. Yeah. Yeah, I mean, if you look in I'm sitting in a study, you know. Yeah, I know what you mean, Mohammed, yeah. However, you know, yes, yeah. Let's hope it clears sooner rather than later. Yeah. Okay, then. So I'll stop there because Pretty must be ready to start, and so I'll pass you over to Pretty. So I'm just going to stop that, come out, back into Teams, and I'm going to say stop the recording. And I'm just going to check for Pretty. And let's go down. Yeah. Okay, so Pretty should be with us, and she'll be able to take over.
Hello everyone. Hope I'm audible.